Hi, I'm Tim, and in this video I'm looking for evidence that the Milky Way has an antihalo. That means a region of increased density antigravity matter around the outside of the galaxy. An antihalo can give the impression of a region of negative density dark matter. For an explanation of the terminology and concepts in this video, see the Antigravity Matter document and the other videos linked to the Antigravity Matter website. A new analysis of the orbital velocities of objects in the Milky Way has been published recently in this paper. The researchers have assumed that they're in a universe that contains gravitationally attractive dark matter. They've estimated the dark matter density profile of the Milky Way and then tried fitting various mathematical models to the data. For people who believe in dark matter, this is important because they want to extrapolate outwards and estimate the total mass of normal matter and dark matter in the galaxy. However, on this channel, we don't believe in gravitationally attractive dark matter. We believe that most of interstellar and intergalactic space contains a thin atmosphere of antigravity matter. The dark matter effects are actually caused by a local reduction in the density of antigravity matter. It's a double negative effect. A prediction from the Antigravity Matter paper is that a typical spiral galaxy is dominated by an antigravity matter vortex like this. The density profile of the interstellar antigravity matter atmosphere should be something like this, with a region of zero density at the centre, a low density region outside that, an increasing density as radius increases, an overdensity around the outside of the galaxy, and then a constant density of antigravity matter throughout intergalactic space. The region of overdensity occurs because the antigravity matter removed from the central region by the vortex piles up around the outside of the galaxy. This is called an antihalo. So here's the orbital velocity graph from the paper, and these are the new data points. As with other galaxies, orbital velocity is fairly constant over a wide range of radii. That's what gives the appearance of a dark matter halo around the galaxy. However, orbital velocity looks like it's starting to fall off more quickly at large radii. The researchers suggest that this might mean the total amount of dark matter associated with the galaxy is less than previous estimates. Note that the researchers haven't published any data in quite a large region around the centre of the galaxy. The Sun's radius is about here. We can do a similar dark matter-based analysis. We take the new velocity data as published. We assume that the apparent dark matter halo is spherical, and we assume that at any given radius, the amount of normal matter in the disk is negligible compared to the apparent amount of dark matter. And we create an apparent dark matter density profile like this. This shows the density of dark matter going slightly negative at large radius. And it implies a total mass of the galaxy of about 1.89 times 10 to the 11 solar masses, if you believe in dark matter. This compares with the 1.81 times 10 to the 11 quoted by these researchers for dark matter only. It's easy to use this plot to create an antigravity matter density profile if we assume that G equals AN equals AA, and the background density of antigravity matter is 2 times 10 to the minus 19 kilograms per cubic meter. And the antigravity matter density profile looks like this. The dark matter line in the middle graph has been flipped over and slid upwards to create the line in the bottom graph. This line does seem to be the shape we'd expect from an antigravity matter vortex. But the maximum amount of density reduction is quite small, much smaller than other galaxies we've analysed in the Antigravity Matter paper and in the video about NGC 1277. However, that's probably because we don't have data towards the centre of the galaxy, where the density reduction would be greater. The region of negative density dark matter has become a region of slight overdensity of antigravity matter. This is the predicted antihalo, though from these data we can't claim it as a conclusive identification. So we can conclude that these new data are at least consistent with the anti-gravity matter theory, and we can make some further predictions. When more orbital velocity data become available for objects closer to the centre of the galaxy, we'll find that the anti-gravity matter density continues to reduce as radius decreases in the shape that you'd expect from an anti-gravity matter vortex. But the reduction in density won't be greater than about 2 × 10⁻19 kilograms per cubic metre. Density can't go negative. And when more orbital velocity data become available for objects further out, the antihalo will become more obvious. That will add more evidence against the existence of gravitationally attractive dark matter, because dark matter density will appear to go more conclusively negative. We haven't added any new terminology, so that's the end of the video. Thanks for watching.